Dear colleagues, we begin the third and last session of our workshop. It is devoted to classical problems and classical application of quantum mechanical and thermodynamical calculation to computational material science. The first our report is a report Alexander Kvashnin and his colleague from Skolkovo Institute of Science and Technology, and it is devoted to computational prediction, synthesis properties, and crystal structure of tungsten boron compound. Please, Alexander.
Okay, thank you for introduction. I hope you see my screen. Good afternoon, dear colleagues. So today I would like to tell you about our big collaborative work related to the prediction, synthesis, measuring of properties, and definition of crystal structures and some other features of the high tungsten boride. And here is the outline of my talk. So first I will tell about the motivation to this work. Then I will briefly explain the results which we obtained during the evolutionary search for stable tungsten boron phases. Then I will move to experimental synthesis of this material with measuring of their properties. And last part will be devoted to a new method which will bring us towards a large-scale synthesis of this new promising material. As you know, there are several types of superhard materials, hard and superhard, and the highest hardness is devoted to the diamond, single crystal diamond, and then the cubic boron nitride with a hardness of 60 GPa goes. But the main disadvantages of this material is they require high pressure in order to be synthesized. And then we can move to another class of materials which is devoted to tungsten carbide and titanium nitride and other compounds of carbide and nitride. So the main advantages of this material is that for their synthesis we don't need to apply high pressures, we need only the high temperatures, but the main disadvantages is a relatively low hardness. And the most promising from this point of view class of materials is transition metal borides. So here you can see titanium diboride or chromium tetraboride with a hardness of about 50 GPa. And again, for their synthesis, we don't need to apply high pressures, only the high temperatures. And due to the ease in synthesis and production, high melting temperature, high hardness, these materials could be used in a wide areas of different applications as well as industrial applications. And if we consider them uh, gas and oil industry, here you can see the drill bit, which usually used to mine oil and gas. And if we consider the cross-section of this equipment, we can find that the cutter of this equipment is mainly made from the polycrystalline diamond or cubic boron nitride, and the base is made of hard alloys like tungsten carbide, titanium nitride. And and the main direction of development in this field is a replacement of traditional materials by new ones, which will have improved properties in comparison to traditional ones. And the most promising system is tungsten boron, because there are many experimental studies which are devoted to synthesis of superhard compounds with preliminary composition of tungsten boron 4. But there are also many theoretical studies which were reported about the compositions of this compound between tungsten boron 3 and tungsten boron 12. Here you can see different crystal structures, different models of this compound. And thus, controversial data about the crystal structure of high tungsten boride leads to unambiguous conclusions about its properties. So we need to define accurately the crystal structure of this material in order to understand its properties. And so we start from the prediction of stable tungsten boron compounds by using the evolutionary search within the crystal structure prediction evolutionary algorithm SPECH, which allowed us to construct the phase diagram shown here in the coordination of enthalpy of formation and the composition, where you can find that we predicted a new compound, tungsten boron 5 here, and it is even stable because it's like on the Conway's hull if we include 0 point energy in our calculations. So our calculation shows that it should be stable at normal condition. It should have unique mechanical properties, as we calculated the viscous hardness of about 45 GPa, which makes this material promising for different applications. Moreover, then we studied temperature stability of this compound. Here you can see we use quasi-harmonic approximation and harmonic approximations in order to understand the temperature range of stability, and found that it should be stable at the whole considered range of temperatures from at least 0 to 215 kelvins, which also makes this material promising for applications in industry. And for successful application of hard material, it should have not only the high hardness, but also the high fracture toughness, because it's another one important property to be successfully applied. So we calculate the HB plot in the coordination of viscous hardness and fracture toughness as shown here. And you can see here that tungsten boron 5 have high hardness and also good fracture toughness. And it lies in the same way between chromium boron 4, the hardest transition metal boride, and tungsten carbide, the most widely used material in the industry. So we found that it should have the optimal combination of these two important properties for successful applications. Then, as we already studied theoretically all the properties, we can move to synthesis. And in collaboration with High Pressure Physics Institute of Russian Academy of Sciences, we performed high pressure sintering of boron and tungsten of the nanometer size powders of these compounds, and obtained the tungsten boron 5 was synthesized. We can obtain these compacts and optimize the experimental setup for this. And then we measure the mechanical properties, the hardness. We measure the Rockwell hardness, and the most interesting is viscous micro hardness. And here you can see the average data across different samples. So here you can see the 22 GPa is for tungsten carbide alloy with cobalt, and 2 samples of tungsten boron 5 compound, which obtained from the high pressure sintering and from arc melting. Here you can see that our samples from 30 to 50% harder than hard alloy based on tungsten carbide and cobalt. But the most question is devoted to composition of this material, because here we write tungsten boron 5 minus X. What was the reason for that? So if you consider the X-ray diffraction pattern of our proposed theoretical model and experimental data, you can find a number of different unidentified low intensity reflections, which shows us that experimental sample should have a high symmetry. And thus, we don't need to consider our high symmetry structure. We need to somehow consider disordered structures in order to accurately describe the X-ray diffraction pattern obtained from experiments. To do this, we propose several models of tungsten boron 5 minus 6 compound, which have these compositions and structures that are shown here. So the compositions of tungsten boron 4.86 and tungsten boron 4.18. And if we consider the X-ray diffraction patterns from these two models, we can see a perfect match between our data and experimental data. Thus, we can make a conclusion that crystal structure of obtained sample is disordered, and composition may vary from tungsten boron 4.18 to tungsten boron 4.86. After that, when we have such kind of average model of disordered compound, we can construct different local structures in order to calculate their formation energy and other properties. Here you can see the boron-rich part of the convex hull, and the red triangles are the local structures which we construct based on the average models, but they have different compositions like tungsten boron 4.2, 4.45, or even higher 4.85, and so on. But and you can see that these structures, they are very close to convex hull, so probably they can be stable when we will consider a higher temperatures. But in order to accurately define the composition which we can obtain in experiment, we need to consider a whole range of the composition from tungsten boron 2 to tungsten boron 5. However, from technical point of view, it is not reliable if we consider DFT calculations, because we need to consider a huge supercells in order to consider different compositions. To solve this issue, we propose a lattice model where we have a lattice of the tungsten boron 3, and we have different sites where we can put the structural units of tungsten boron 3, and the triangles of boron is the key element of tungsten boron 5, and thus we can calculate the total energy by using this simple empirical formula where the coefficients of interactions were fitted according to several hundreds of DFT calculations, and thus we can do a brute force search for stable compositions from tungsten boron 3 to tungsten boron 9. So thus we check about several millions of the structures, and we easily can calculate the convex hull, which is shown here. So these blue points, they're devoted to our lattice models. And you can see here that we potentially may obtain the wide range of the compositions that may be formed during the synthesis at high pressures, which is confirmed our experimental data that we obtain the mixture of different compositions. Thus, we called our material tungsten boron 5-X. Then let's move to another step, to optimization of the synthesis of tungsten boron 5-6, as this compound possesses really high properties for different industrial applications. So the main disadvantages of methods which usually used to produce transition metal borides is like high pressure sintering or SPS techniques, because they need to use either vacuum or high pressure. So it increases the price of production of this material. So thus we would like to propose a new vacuumless method. So the experimental setup is shown here. So I will not go into details to this experimental setup, because I'm usually do here a theoretical work, and this was done by our colleagues from Tomsk Polytechnic University. And then we try to optimize the parameters of this experiment in order to obtain the big amount of tungsten boron 5-6. So first we vary the atomic ratio of tungsten to boron from 1:1 to 1:20. Here you can see that we obtain different amount of tungsten monoboride, tungsten to boron, tungsten boron 2, and a very small amount of tungsten boron 5-6. But from this point of view, the optimal parameter is 1:15. So it's here where we obtain about 15% of tungsten boron 5 in the mixture, and then we should optimize another parameters. So here we have 4 more parameters. One of them is arc duration, as we have arc reactor. Then we have change the duration of arc plasma, and by using the arc duration of about 15 seconds, we can obtain easily the 50% of tungsten boron 5, as you can find here. Then we also can vary the electric current, and you can see here that if we increase the electric current, the amount of tungsten boron 5 decreases. So the optimal value for this parameter is about 60 ampere. And then we also can vary the mass of the initial powder of tungsten boron, which we can load in our experimental equipment. And if you can find from this, if we use 1.5 gram of initial powder, we will obtain the high amount of tungsten boron 5 of about 60%. So thus, for our experimental setup, we obtain the optimal parameters for effective synthesis of our new material. So it is atomic ratio of tungsten to boron, initial powder mass, electric current, and arc duration. And using these parameters, we can easily synthesize the powders of tungsten boron 5-6. Then we perform the analysis using scanning electron microscopy, transition electron microscopy, in order to understand the morphology of obtained nanoparticles. And after that, we can measure the weakest hardness of two obtained samples. So first sample was obtained with the 50% of tungsten boron 5-6 in our sample, while the rest of the volume is tungsten boron 4. And the second sample was with the highest amount of tungsten boron 5, about 67%. And here you can see the measured weakest microhardness for different loads, starting from 0.1 Newton to 1 Newton in comparison with tungsten carbide. Here you can see that our data, they very well agree both with the different empirical models which used to calculate hardness, as well as with some reference papers where people obtain samples of tungsten boron 4, as they call, using SPS techniques with a little bit higher quality, but still this method is really expensive and it's not obvious how to perform large-scale production of this material using SPS or other techniques which requires high pressure or vacuum. And our method is cheap, effective, and we can produce the same quality material using our technique. So that's almost it what I want to say. And in conclusion, I would like to recap the main points. So first, we performed the evolutionary research in order to predict new material in tungsten boron system. So we predicted tungsten boron 5, which potentially should have unique mechanical properties. Then we performed high pressure sintering experiments in order to synthesize this compound and found that indeed it should have a high hardness and potentially can be used in different types of industrial applications. And after that, we would like to optimize the synthesis process of this unique material and propose new vacuumless technique, which allowed us to produce samples, let's say large-scale samples, with the same quality, the same hardness, which can be potentially will be used further in different applications. So I would like to acknowledge my colleagues who contribute to this work and funding agencies, and also you for your attention.
Thank you, Alexander, for interesting report. As I understood, your colleagues tested your compounds.
Yeah.
Any questions? My questions. The phase diagram of the tungsten boron system was experimentally studied back in the 60s, but the phase reached in boron contained only 4 boron atoms. Has a new version of the phase diagram of the system, no pressure temperature concentration diagram, including compounds with 5 boron atoms been experimentally studied?
Yes, thank you for question. This is a really interesting question from the point of view that tungsten boron 4, it's incorrect composition, incorrect notation of the compound. If you will consider tungsten boron 4, it should have different crystal structure than that people experimentally produced. So actually, tungsten boron 4 phase, which was produced for 60 years, it is exactly the same as tungsten boron 5-6. And the main advantage of our work is that we finally understand the crystal structure of this compound. So it shouldn't be tungsten boron 4 because it should be tungsten. It could be called tungsten boron 4 plus X or tungsten boron 5-6. But the crystal structure, but the type of crystal structure is devoted to tungsten boron 5, which we predicted theoretically.
Oh, thank you. The next questions. Thank you, Alexander. The next report is a report of Alexey Voskov from Moscow State University, and it is devoted usage of robust regression for approximation of thermodynamical data. Please, Alexey.
Hello, can you see the screen?
Okay.
Okay. So And I can't enable my video also.
Okay.
It's okay.
No. Так.
Yeah, now we see your presentation, Alexey.
It's okay.
It's okay.
Okay, so good evening. My topic is usage of robust regression for approximation of thermodynamic data. When we approximate existing thermodynamic and other data, there is one serious issue, problem of outliers. Outliers are points that can seriously distort your results. For example, here is the example. You see some points that are lying almost on the straight line, and you can also see some outlier that lies outside it. And when we try to approximate it by the least squares method, the result is on the very strong influence of these outliers. Our conventional approximation procedures, such as mean values or the least squares method, that are very commonly used, they are all based on assumption of normal distribution of input data, and they are sensitive to even rather small deviations from such hypotheses about statistical properties of our input data, and they are sensitive to outliers. This problem has several possible solutions. The first one, we can throw out outliers using either some physical or intuitive, intuition, or use some statistical criteria. For example, studentized residuals of our points and detect our outliers. The second approach that allows to reduce its influence is use the weighted least squares method. When we use reduced weights for the less accurate data and for possible outliers, their influence will be weaker. If we, for example, will apply low statistical weight to the outlier on the linear plot on this slide, of course it will reduce its influence. But there is also a third alternative, using so-called robust method that use special objective functions that automatically reduce the influence of outliers and non-normality of our input data. For example, we can use the median instead of mean values, or use the least absolute deviations method instead of the least squares method. Sometimes there is an impression that these methods are something new. No, they are actually a very old method. Robust regression based on least absolute deviations was suggested more than 200 years ago by Roger Joseph Bachovich. He suggested use the least absolute deviations method. It was earlier than the least squares method discovered by Gauss. But due to computational complexity, its further development began after development of computers. I mean, in last century. When we talk about outliers and robust regression, we will often use so-called contaminated normal distribution that was suggested and researched by John Tukey in the middle of 20th century. Contaminated normal distribution resembles normal distribution, but it has two terms. So we return to the contaminated normal distribution that is shown on this slide. The first term is just as ordinary normal distribution, the same probability density function, some mean value, some variance, and some weight, 1 minus alpha, that is very close to 1. But the second part is another normal distribution that has much higher variance. This distribution has two parameters, lambda and alpha. Alpha means fraction of contamination, and lambda means the variance, the relative standard deviation of this contamination. It is useful to model data sets with outliers. Let's show a real example of contaminated normal distribution in experimental data. Let's take isobaric heat capacity data of natural light. On the heat capacity with temperature plot, everything looks okay. But when we build scatter plot for relative deviations, we can definitely see the contamination. Low temperature data with higher uncertainty, and some points have much higher uncertainty. If there is also visualization based on empirical cumulative distribution function that is on the right of this slide. The x-axis is our relative deviations, and the vertical y-axis is fraction of points that have the relative deviation below it in special coordinates. The most important thing in this nonlinear coordinates is that normally distributed data sample will look like as a straight line, and we see such straight line in the center, dense straight line. But contamination gives also another parts of this plot with other slope, and this slope corresponds to much higher variance. So if we build such quantile plot or empirical cumulative distribution function in nonlinear normal nonlinear reverse cumulative distribution function, we can detect it visually. Of course, in this case, there are many points. They're symmetric, and if we use the least squares method, they will compensate each other. But what if we will have just upper point? It can distort our results. And to overcome the problem of outliers, we can use so-called M estimators. M estimators are based on such sum. When R are residuals and ρ is loss function, it's evident that the least squares method is just a specific case of M estimator. We just take ρ function as square t and obtain the least squares method. Or we can take other function such as absolute value and obtain the least absolute deviations method. Sigma is scaling factor. It's important for some loss functions that depend on scale of our data. Beta are vector of model parameters to be optimized. M originates from the maximum likelihood method. If we write likelihood function for some distribution and take logarithm of it, Such algorithm, after some linear transformation, will lead us to the M estimated with some cost function. For example, least squares method correspond to normal distribution, and the least absolute deviations method correspond to Laplace distribution. And aim of this work was applying robust M estimators for approximation of heat capacities and heat contents of individual substances. Petalite and potassium substitute natural light will be used as an examples. The M estimators were added into CPFIT program. This program approximates thermodynamic functions of individual substances by the weighted sum of Einstein functions. So we have several alphas, weights, and several thetas, and several Einstein temperatures. In new version of CPFIT program, the arbitrary M estimators were added. They were added by extension of our CPFIT kernel, by addition of special API for interactional nonlinear optimizer. Older version of CPFIT used Levmar library that is designed exclusively for the least squares method. And now it may use also custom library that implements M estimator based algorithm. To estimate parameters of the model, we begin with the initial approximation based on the least squares method, then estimate our scaling factor using a robust estimation of standard deviation. After it, we can find alpha and theta using robust method, and if we want to make the estimation more accurate, we can reassess scaling factor using obtained robust estimation and repeat this procedure. In this work, the next experimental data were used. For potassium substitute natural light, only heat capacity data obtained by diabatic calorimetry were accessible. These data have a lambda transition with this transition temperature. In the case of petalite, we have data for both heat capacity and heat content data for higher temperatures. And these data have two outliers at very low temperature. If we don't exclude it, the least squares method won't give us good approximation. Let's talk a bit about the method used by inside a new version of CPFIT. It's so-called iterative reweighted least squares method. This method is a generalization of Gauss-Newton method for M estimators. It was suggested in the Soviet Union by Mudrov and Kushko for approximation of orbits of artificial satellites. The first two assumptions are very similar to the Gauss-Newton method. We replace our residual functions into its linearized form based on Jacobian matrix. And after it, we write necessary conditions for the minimum of objective function, equations with its derivatives, and try to solve its derivatives using Newton method. In the of course, it can be rewritten in the matrix form, but this matrix form has a very serious drawback. It will require second derivatives for our loss functions, and they are not always accessible. we can use, the third assumption is approximation of the second derivatives using the first derivatives and so-called weight function. Such approximation will turn our system of linear equation into the system of linear equation similar to the weighted least squares method, with the weights that are controlled by the weight function. This can be combined with the Levenberg-Marquardt or Trost-Rager and Dirichlet methods. We used three weight three loss functions and corresponding weight functions. Here is the table with some examples of commonly used weight functions. For example, least squares method has square function. Huber function is some piecewise composition from the list absolute deviation method loss function and quadratic function. And there is also, and the third weight function that we used, Andrews sign function, is so-called redescending loss functions that is not convex. If we look at weight function, it can just exclude outliers, but it is not convex. And it may cause problems with convergence. Here is the first result: approximation of experimental data for potassium substitute natural light. We can see that if we try to model with four terms, four Einstein functions in all cases, and we see that attempt to apply the least squares method causes oscillations. We can see it on the left plot, but we also can see it in the center, but it's just less visible. If we use Huber function, oscillation became lower, and Andrews function cause even lowest oscillations. We can see the table on the bottom with obtained standard deviation of approximation, standard error of our models. There are two kinds of its estimation. Just compute standard deviation and use so-called K-folding procedures, the K равно 5. We can see that in the case of K-folding procedure, standard deviation is higher, but the model is still not overfitted. In the case of petalite, we have both heat capacity and heat content data. And if we apply least squares method, we can see huge oscillations, and further attempts to increase number of terms model causes variable conditions problem and program termination. Huber and especially Andrews model allow us to get rid of use of estimation. In the case of Andrews sign loss function, it is especially beneficial for approximation of high temperature heat contents. We can see that it gives much less systematic error. And applying of K-folding to our models also confirmed that there is no significant overfitting. So the conclusion are present on this slide. The suggested procedure was successfully implemented in the superfit program, applied to potassium substituted natural light and petalite, and both Huber and Andrews sign loss function allow to automatically decrease influence of both outliers and narrow lambda-shaped anomaly. And Andrews sign loss function decreases influence of outliers stronger than Huber loss function, but it's more sensitive to the initial approximation. Of course, the robust regression can't replace human expert, but it's a useful instrument. Thank you for attention.
Thank you, Alexey, for interesting message. And my question. Robust regression methods are designed to analyze data containing outliers. Is it easy to identify such outliers, for example, by means of an expert assessment and exclude them from the analyzed set, and then apply classical regression analysis? Давайте по-русски. Дело в том, что робастные методы предназначены для обработки данных, которые содержат выбросы, как вы говорили. И это нарушает условия центральной предельной теоремы, которая вот определяет нормальность, очень важный параметр для дальнейшего статистического регрессионного анализа. Не проще ли просто взять, провести экспертную оценку ваших данных, выбросить вот эти выбросы, которые часто связаны с ошибками, и дальше применить обычный классический регрессионный анализ?
Oh, thank you for the question. I think that both approaches are valid, and I think that exclusion of our outliers by expert will give even lower variances and lower confidence intervals of our parameters. But there is an issue. Such outliers aren't maybe not too evident, especially in the case, for example, of multidimensional regression, or for example, let's I can show example from presentation with example of such advantage. Видна ли презентация? Can you see it?
Okay.
Okay, видно? Хорошо. So we can see that, for example, we see the situation with such heat capacity anomaly, and of course we can and we probably we must exclude it manually for the better accuracy. But there is always a question: where are the borders of such anomaly? If we apply, for example, least squares method, we probably should make several attempts. I tried to approximate it by the least squares method, and I had to make multiple attempts. In the case of applying robust regression, it can show such outliers and such peaks more evident, even on plots. It may make work of an expert easier.
Okay, next question. Oh, thank you, Alexey. The the last report of our workshop is the report Tao Fan from Skolkovo Institute of Science and Technology, and it is devoted to LCON2, a program for calculating transport property quickly and accurately.
Can you hear my voice?
Okay.
Okay, thank you.
Yes, it's very nice.
Good afternoon, everyone. My name is Tao Fan from Skolkovo Institute of Science and Technology. My speech is Icon, a program for calculating transport properties quickly and accurately. I developed this program aims for calculating thermoelectric materials. Thermoelectric material is a kind of functional material which can convert heat to electricity or vice versa. No matter in which condition, one key parameter for thermoelectric material which decides the energy conversion efficiency is this figure of matter ZT, which includes step coefficient, electric conductivity, temperature, and thermal conductivity. Well, for thermal conductivity, it includes two parts, from the contribution from electron and the contribution from lattice vibration. The objective of thermoelectric research is to improve these ZT values. For now, it's usually 1 to 2. The aim is to increase it over 3 or 4. So let's look at this formula of ZT. Generally, the variables compose this ZT can be divided to two parts. So for phonon transport property kappa L and electronic transport property alpha, sigma, and kappa E. For kappa L, I proposed the modified by Kelvin model, and for the electronic transport properties, well, I found it can be calculated based on perturbation theory and Kanban model under the relaxing time approximation. The detailed description of the model was written in these two papers. If you are interested, you can check these two papers. And all these models has been implemented in my program icon, which means AB initial conductivity calculation. Here I want just to give you a short introduction about the model behind the program. So for first about the electronic transport properties, well, according to the relaxing time approximation, all the transport coefficient can be expressed as a function of this variable. Here, tau is the relaxing time of electron, Z is the reduced band energy, F is the Fermi-Dirac distribution function, M is the effective mass, and K is the wave vector. L and Q just a constant. You can understand this formula like sampling and energy average of the relaxing time as a function of energy, band energy. So by using this formula, the relaxing time was transferred from a function of energy to a function of chemical potential, and the chemical potential were related with carrier concentration. So the problem is how to calculate this relaxing time tau. Well, let's consider the scattering process electron should have been through. Well, according to the Matheson's rule, the total relaxing time of electron should be the addition of the all scattering process, which include acoustic phonon scattering, optic phonon scattering, impurity ions, boundaries, etc., etc. For every scattering, the formula for each of them could be very complex. For example, for scattering from phonons, in order to compute it, you need a very dense sampling in the reciprocal space for both electron state and phonon mode. So it could be very time consuming and resource limited. Luckily, we have we have simple model to calculate it. Let's take the scattering from acoustic phonon example, which can be described by the formation potential theory proposed by Vadim. The basic assumption behind this theory, at least here, Vadim proposed this theory aims for calculate the mobility of nonpolar semiconductors like silicon. In order to apply this theory to a wide range of material, it need to be this theory need to be extended. For example, usually the material degenerate because of doping, and the energy bands usually not the parabolic, especially near the boundary of Brillouin zone, and also the effective the energy constant energy surface are not exactly sphere, and it should be the ellipsoid constant energy surface should be more common. So the first step is to establish the relationship between the wave vector and energy, which we usually use a kind band model. This is for conduction band minimum or valence band maximum. We can express the band relationship like this. Here the vertical and the parallel symbol indicating the direction of the transverse and the longitudinal direction of constant energy surface, and epsilon is the band energy, epsilon g is the band gap, and then we can write the energy dependence of effective mass and the density of state. Here MD is the density of state, effective mass. Well, by using this kind band model, we can rewrite the formula proposed by Vadim. So here is the result, and the part outside the bracket is the usual formula proposed by Vadim, and the part in bracket is kind of non-parabolic correction to the original parabolic model. Well, for other scattering process, I think the results are similar. I mean, in our program, I only can include scattering from acoustic phonon, polar optic phonon, and ionized impurities. Well, for light thermal conductivity calculation, generally there are three kind of methods for such a calculation. Each method has its pros and cons. For icon, it's based on the Debye-Kelvin model. The original Debye-Kelvin model will generally say it's also aims for calculating the property of isotopic semiconductors like silicon. Morelli gave specific formulas for three acoustic phonon branches. Yes, these formulas might look very complex, but actually many parameters included are just constant, or you can be easily obtained. So only three parameters need to be calculated carefully: is this gamma, Grandson parameter, and the phonon velocity v, and also characteristic temperature of each phonon branch theta included here. So previously, these three parameters need to be obtained from experimental measurements or fitted from experimental data, but now they can be calculated from density function theory directly. Well, furthermore, I updated the formula by including the contribution from optic phonons, because at the temperature above the Debye temperature of compounds, all phonons will contribute to the light thermal conductivity. So this is the updated formula, and for kappa O, I use Einstein model instead of Debye model to calculate its specific heat, and the formula for relaxation time just assume the same as acoustic phonons. Then the next question is probably how these models behave. Is it good? So here I will show some testing data. This page shows the test for the mobility, and this table lists the compounds used to test, and also the doping, including both N-type and P-type materials. The temperature and the character concentration corresponding to the experimental conditions, and the calculation run at the same condition, so the results can be compared. And this two-page shows the results of mobility. Generally, I can say the calculated value is close to the experimental value. For some compounds, the calculated value agree quite well with experimental results. But for some compounds, the results it's a bit different, show a lot difference. Actually, it seems our model can be applicable for a wide range of materials. For example, this N-type gallium arsenide, which has a very large mobility. You see the calculation and experiment agree quite well. For P-type copper aluminum oxygen, it has the lowest mobility in the testing materials. Although the calculated value is a bit large difference at low temperature, but yeah, the difference becomes smaller with increasing temperature, and still the whole value is in the same magnitude with order magnitude with the experiment. And this is the testing for the stable coefficient, and this 2-page shows the results. For stable coefficient, well, the calculated value are quite close to the experiment values. And this page shows lattice thermal conductivity results. For this temperature testing set, I try to include as many as elements and make the site as diverse as possible. Also, the testing material the kappa value covers a large range. And here I show the compounds and also the results at room temperature. Let's plot this data in a figure. I use 2 indexes to quantify the relationship between experiment and the calculation. The first index I use is Pearson correlation coefficient, which indicating the linear correlation between 2 variables is 0.9999, which means the calculation and the experiment has a very strong correlation. Another index I use is this room mean square relative deviation, which is a mirror of quantitative difference between 2 variables. Its result is around 50%, which means averagely the difference between the calculation is 50% difference with respect to experiment values. So from the figure we can see for compounds with medium and large lattice thermal conductivity, our model matches quite well. Well, for compounds with small kappa, especially for compounds with value less than 2, well, our model tend to underestimate the results. So this is a place I need to be improved in the future. This page shows the testing result for diamond and silicon compared with experiment and for AB initial calculation. As you can see, our model can give a very good result compared with experiment. And yeah, this page here, I just want to show you an example about using an icon to screen the thermoelectric material. Well, this is a project we are working on. The object is the chalcogenide, mainly focused on the chalcogenide thermoelectric materials. I extracted all structures from the material project, and the selective standard as follows. So based on the results of part of the cubic compounds, yeah, a paper was published recently, and here these two pictures shows a summary of the calculating results. The left for N-type, the right for P-type. As you can see, the y-axis represents the maximum power factor value a compound can reach, and the x-axis corresponding to the carrier concentration that's related with this maximum power factor value. Well, so for compounds with their maximum power factor value higher than 10, I will think this compound as are promising, and they will go forward to calculate their lattice thermal conductivity and also their figure of merit. As you can see, some representative compounds were marked in the pictures. which included some, for example, lead tellurides, germanium tellurides. These are very already well-known thermoelectric material. So this really validates our method. And this page, in this page, I list all the compounds which have their maximum ZT larger than 1. So the first 7 compounds belongs to, they have the same structures, and the characteristic of this compound is they have very large Paul factor values. Some could even beyond 100. Just remind that the state-of-the-art thermoelectric material like bismuth telluride and lead telluride, their Paul factor are just 30 to 50. So this is quite promising. And the only N-type compounds, at least just this germanium selenide, which have a relatively high Paul factor value, but extremely small lattice thermal conductivity. So it has a ZT value larger than 1. And interestingly, recently I found a paper just published, and they found the same compound as I did, but using different method. So this could also improve the efficiency of my model. Well, thanks for listening. I welcome questions.
Please, questions. My question. Taking into account the importance of calculation, for example, of latest thermal, latest thermal conductivity for the search for new effective thermoelectrics, I would like to ask about the accuracy of this calculation for example, for semiconductors. I saw the ZT about 7 with compounds. Compounds with actinium, very interesting object for thermoelectrical materials with radioactive element. What is your accuracy of your calculation? I saw the deviation, for example, for industrial thermoelectrical material with telluride is a very large deviation. What is this? What? The error of calculation of such the T for this compound.
I'm not sure where you see the large difference of the ZT, because as I see, I mean, just compare the Paul factor values of this already well-known thermoelectric material like lead telluride and germanium telluride, and etc. I think the accuracy is okay, it's acceptable. I think for my for my method, I'm not trying to accurately calculate the transport properties of these thermoelectric materials. My main objective is to find a way to fast screen the promising compounds from thousands or 10,000s of compounds, and then we can the next step we can use more accurate methods such as 4AB initial calculation or even experiment to continue the study. And for my thus for this screen objective, I think my methods give show a very reliable results, accuracy. Both efficiency and accuracy. Yeah.
What is compound cadmium selenium 2? I know compound cadmium selenium.
Well, I think this is the structure from a material project. As I remember, I show here from the material project, its energy about convex Hall is 0, so which means this compound is is stable, but it doesn't mean it's common in the nature field. Perhaps this, yeah. So I think this just means this compound could be make in the nature in the real world, and if you make it, and I remember I just yes I mentioned this paper which said they also find this compounds. I mean, seems they already made these compounds in the experiment, and there is some evidence, yes, so it can exist.
Next question, Listen, Vyacheslav, please.
I have following question because it seems a bit not clear for me. You say that you predict existence of some compounds,
Yeah.
but we'll probably get the energy of formation of this compound in terms of Gibbs energy. But I have not seen in your presentations the relative stability of the compounds depending on composition and temperature. My point is that depending on the relative stability, not just stability of a compound, but the relative stability, the compound can be either stable or metastable, which also can mean that it's very hard to form. Probably it will not be as stable as we want it to be, or it can be absolutely unstable. So did you compare, did you analyze the relative stability of the compounds you find?
Yeah, actually, I think what you mean is this E about how data I show here. No, this is how to say convex Hall the energy.
No, I don't mean convex Hall. I mean Gibbs energies.
Gibbs energy. Well, at this step, I haven't do such a calculation yet. Because
I mean, this would be the most important thing to understand if this compound can be formed at all.
Yes, I agree. Yeah, but I think for my job, it's I think usually this as long as this energy above Hall is lower than 0.1 electrovoltage, it's highly possible to be synthesized or exist in experiments.
It does not matter if the relative stability of the compounds competing with the compound you are forming are more stable, then you will never form your compound.
Yes, this is a problem in the next step. I mean, when you get this promising compounds, you want to make it in experiment, you need to check these relative compounds. But for me, my job is first to find which compound is promising. I mean, they have the potential to ZT value larger than 1. This is my objective to do this work. I agree with you. Yeah.
I have another question. Looking at this ZT, actually my question is relating to the previous one. Looking at ZT, which you list in tables, and very high ZT in actinides, how do you think that's something? What makes different in this specific compounds that they have so high ZT? Do you understand any physics under it?
You mean for this compound?
Yeah, for example.
Yeah. Okay, from the computational aspect.
No, not from calculations, from physics.
From physics, it's because it has a relatively good electronic conductivity and very low lattice thermal conductivity. I think it's because of this because they contain this actinium atoms. It's a radioactive atom, and it makes the crystal has a very strong anharmonicity. So their lattice thermal conductivity very low. It's as I remember, its value at 300 Kelvin could be lower than near 1. So yeah, it makes the RZT value very high. But since this compound is radioactive, I admit actually, yeah, it's just I mean, computational sense. For in experiments,
Do
yeah,
you want
maybe.
to say that the other elements having such properties, similar properties, will give the same results?
You mean the compound with strong?
Oh, I mean also actinoids.
What?
That doesn't look to be right. Okay, fine. Some more questions probably?
Any questions? Okay. Thank you, Tao Fan, for interesting talk about thermoelectric materials. I hope that you will be Nobel Prizer for this compound, because the usual freezer, we change it to thermoelectrical freezer. Okay, thank you. This report was last on our workshop. I would like to thank the organizing committee of the conference for the good organization of our workshop, and Alexandra the first and Vladimir the first. Our workshop was this year we are meeting for the second time. At the meeting, reports were presented on the most important aspects of computer material science, from quantum mechanical and thermodynamical calculation to machine learning. It is very pleasant that the geography of participants is very wide. Researchers from China, Japan, Russia, Italy, Germany, France, Great Britain, we are taking part in the meeting. On behalf of program committee of our workshop, I would like to thank all the speakers for interesting report. In my opinion, we managed to combine the variety of areas of computer material science and a little to analyze the possibilities and ways of further development of this important area of science. Unfortunately, the pandemic did not allow us to communicate offline, but I hope that our next meeting will be in more good mode. Thank you, everyone.